Welcome to the Sleepy Scholar. It's lovely to have you here tonight. Wherever you are right now, however you've arranged yourself for sleep, I want you to know there's no rush. None at all. Maybe you're under a heavy blanket with the weight of it pressing you down into the mattress. Maybe you've got a lamp still glowing somewhere across the room, a soft little island of light you haven't quite decided to turn off yet. Maybe you're on a train or a couch or the far side of a long day and you just want a voice to hold the dark for a while. Whatever it is, you've found the right place. Settle in. Let your shoulders drop. We're going somewhere very far away tonight, and we're going to take our time getting there. Before we begin, where in the world are you watching from tonight? I always wonder, somewhere it's late afternoon and the light is going gold. Somewhere it's the dead middle of the night and the whole street is asleep. But I'd love to know if you feel like leaving it in a comment before you drift off, your corner of the world, and what the hour is there right now. And if you enjoy these slow journeys into space and want more of them, a quiet like and subscribe genuinely helps this sleepy little channel keep going. Small creators like me really do rely on it. And to those of you already here, already subscribed, already part of this nightly ritual, thank you. Truly, it means more than you know. Now let's begin, shall we? I'm going to start with something I find almost impossible to believe, even though it's true, and I've sat with it for a long time. Right now, tonight, while you lie there getting ready to sleep, our galaxy is eating another galaxy. Not in some distant future, not as a warning of things to come. Right now, the Milky Way is very slowly and very silently devouring a smaller galaxy whole. And the strangest part, the part I want you to carry with you into sleep tonight, is that it's one of the gentlest things in the whole universe. Let me tell you about the evidence, because the evidence is written across the sky above your roof at this very moment. There's a galaxy out there, a small one, a dwarf galaxy, far tinier than our own. And our Milky Way has been pulling it apart over an enormous stretch of time. As it pulls, it stretches the little galaxy's stars out into a long, thin ribbon, a river of stars. And that ribbon of stolen stars has been drawn out so far, wound so completely around our galaxy, that it now wraps more than 360 degrees, all the way around, completely around the entire Milky Way. A single dying galaxy smeared into a loop of light that circles our whole home galaxy like a ring around a planet, except made of stars and made of the slow undoing of something that used to be its own little world. It is one of the largest coherent structures of stellar debris we know of in the entire galaxy. Think about that word for a moment. Debris. The leftover scattering of a thing that was once whole. And it goes all the way around. Now here's the part that I find tender rather than frightening, and I want you to feel it that way too. You might imagine that one galaxy eating another would be a catastrophe, a crash, a collision of unimaginable violence, billions of stars smashing into billions of other stars in a great cosmic fireball. But it isn't like that. It isn't like that at all. The truth is much stranger and much softer. When two galaxies pass through one another, and they do pass through one another, right through like one cloud drifting through another cloud, almost no two stars ever touch. Not a single collision in most cases. Nothing burns. Nothing shatters. Why? Because stars are so unimaginably far apart. The space between stars is so vast, so empty, so generous with its distances that two entire galaxies can slide straight through each other and the stars just miss every one of them. They pass each other in the dark with room to spare, like two swarms of fireflies drifting through the same field on a summer night, neither one bumping the other. The galaxies feel each other only through gravity. that quiet, invisible pull, and it's gravity that does all the work. Gravity stretches, gravity tugs, gravity pulls the little galaxy slowly apart over millions and millions of years. But there is no crash, there is no fire. The devouring is not a collision. It is a slow, soft, gravitational unraveling. Silent, patient, almost gentle. I think that's a lovely thing to hold on to as you lie there. The biggest acts of consumption in the universe, galaxies eating galaxies, happen without a sound, without a single star ever being struck. They happen the way a tide comes in, the way frost spreads across a window overnight. You'd never hear it. You'd never see it move. And yet it's happening right now, above you. So let me introduce you, properly and slowly, to the galaxy that's being eaten. Its name is the Sagittarius Dwarf Spheroidal Galaxy. Astronomers who love their shorthand often just call it SGR-DSPH, but you don't need to remember that. Just think of it as Sagittarius, the little galaxy, the one being slowly taken into ours. A dwarf galaxy meaning a galaxy far smaller and far dimmer than our own. A faint, modest thing compared to the great spiral wheel of the Milky Way, and it is, as we speak, in the act of being absorbed. Here is something that I think tells you everything about how quiet this whole process is. We didn't even discover this galaxy or this enormous neighbor, this whole other galaxy being devoured right next to us, until 1994. That's astonishingly recent when you think about it. There are people listening to me right now who are older than our knowledge of this galaxy. We had sent spacecraft to other planets. We had mapped the far reaches of the cosmos, and yet a whole galaxy, one of the very closest galaxies to us, was sitting there undiscovered until just a few decades ago. 3 astronomers found it: Rodrigo Ibata, Gerard Gilmore, and Mike Irwin. They published their discovery in the journal Nature in 1994, and with it they handed us one of the clearest, most intimate views we have of a galaxy in the act of dying into another. And you might be wondering, how do you miss a galaxy? How does a whole galaxy stay hidden? Well, here's the reason, and it's a beautiful one. Sagittarius was hiding behind something. It lies on the far side of the galactic center, the far side of the great glowing heart of the Milky Way, that dense, crowded core where the stars pile up thick and bright. Imagine trying to spot a single candle on the other side of a bonfire. The bonfire's glare drowns it out. That's what happened. Sagittarius was tucked away behind the busy, crowded star fields of our own galaxy's bulge, lost in the glare of the galactic center on the opposite side of it from us. We were looking right toward it the whole time, and our own galaxy's brightness was standing in the way. It's quite close in cosmic terms. Sagittarius sits roughly 65 to 70,000 light-years from our Sun. Now a light-year is a distance. The distance light travels in a year, and light is the fastest thing there is. So 65,000 light-years is a vast, almost unthinkable gulf. But in the scale of galaxies, in the scale of the universe, that's practically next door. It's one of our nearest galactic neighbors, and it was hiding in plain sight behind the heart of our own galaxy until 1994. Now I want to slow down here, because this is the heart of the whole story, and I want it to land softly. Sagittarius is being torn apart right now, not in some far-off age. The tidal forces of the Milky Way, and I'll explain exactly what those are in a moment, are stretching it apart on each orbit, pulling streams of its stars out ahead of it and behind it, like trailing threads pulled loose from a sweater. This is not a future event. It is a present one. It is happening tonight as you fall asleep, exactly as it was happening last night, and the night before, and as it will be happening long after we are all gone. Let me explain what a tidal force is, because it's gentler than it sounds, and once you understand it, the whole picture clicks softly into place. You already know tides, the rising and falling of the sea caused by the moon's gravity tugging on the Earth's oceans. The reason tides happen is simple. Gravity is stronger when you're closer to something, and weaker when you're farther away. So the side of the Earth nearer the moon gets pulled a little harder than the side facing away. That difference, that little tug of war between the near side and the far side, is a tidal force. It's not the pull itself, it's the difference in the pull across the width of a thing. Now imagine that same effect, but on a galaxy. The little galaxy, Sagittarius, swings close to the great Milky Way. The side of Sagittarius nearest to us gets pulled a little harder than its far side, and that difference, that stretch, pulls it apart. The near edge wants to fall toward the Milky Way faster, the far edge lags behind. So the galaxy elongates, it draws out, stars peel away from the front of it, racing ahead, and stars peel away from the back of it, trailing behind. Leading streams and trailing streams, two long tails of stars drawn out of the little galaxy like taffy stretched slowly between two hands. That's how a galaxy comes apart, not in a crash, in a stretch, a long, slow, gentle pull, repeated over and over, each time taking a little more. And it does happen over and over because Sagittarius is in orbit. It goes around the Milky Way, the way the moon goes around the Earth, the way the Earth goes around the Sun, though far, far more slowly. Sagittarius completes one orbit of our galaxy roughly every 550 to 750 million years. Say that to yourself slowly. Somewhere between 550 and 750 million years for a single trip around. A single lap. The dinosaurs came and went in less time than a couple of those orbits. Whole eras of life on Earth, whole chapters of geology rise and fall in the span of just one of Sagittarius's loops around our galaxy. And on each of those enormous loops, every single pass, the Milky Way takes a little more of it. Each orbit, more stars are stretched away into those long ribbons. Each passage whittles it down. So this little galaxy has very likely completed several of these passages already. Several trips around, several times being stretched and pulled and shedding its stars into the dark. And it has been losing stars each time. It is smaller now than it was. It will be smaller still after the next pass. In fact, what's left of Sagittarius today is only a remnant, a shadow of what it once was. The models, the great simulations astronomers run, where they let computers play out the slow gravitational dance over billions of years, suggest that Sagittarius began far more massive than it is now. A much bigger, much fuller little galaxy with many more stars held within it. And over billions of years of these slow passages, it has been whittled down, stretched out, distorted, reduced. What remains is a stretched and warped leftover, a galaxy caught in the long, quiet middle of its own undoing. Not dead yet, not whole anymore either. Somewhere in between, in the act of becoming part of us. I find there's something almost peaceful in that. This isn't a sudden death, it isn't a violent end, it's a slow surrender spread across a span of time so vast that on any human scale, on the scale of your whole life, on the scale of all of human history put together, it does not appear to move at all. If you went outside tonight and looked toward Sagittarius, and then went out and looked again in 1,000 years, you would see no difference. None. The galaxy would seem perfectly still. And yet it is being taken apart thread by thread, in the longest, gentlest unmaking you could imagine. Now, let me tell you something about this little galaxy that I think is genuinely delightful. One of those facts that once you hear it, you can't quite stop turning over. Because Sagittarius didn't come empty-handed into this slow meal. It brought things with it. It carried, within itself, several globular clusters. Let me tell you what a globular cluster is gently, before we go on. A globular cluster is a tight, dense ball of stars, hundreds of thousands of them, sometimes more, all bound together by gravity into a roughly spherical swarm. Imagine a great glittering snow globe of stars packed close at the center and thinning toward the edges. They're very old, these clusters, among the oldest things in any galaxy. Ancient gatherings of ancient stars, and Sagittarius, this little dying galaxy, carries several of its own. And as the Milky Way pulls Sagittarius apart, it doesn't just take its loose stars, it inherits its globular clusters too. The little galaxy is donating them, handing them over, scattering them out into the great halo of stars that surrounds the Milky Way. So our galaxy is quietly inheriting the dead galaxy's treasures. The jewelry of a galaxy that no longer fully exists passed along to us in the slow act of being consumed. And one of these globular clusters has a name and a story I want to give you, because it's perhaps my favorite small detail in all of this. The cluster is called M54, and M54 sits at or very near the very center of the Sagittarius galaxy, so close to its heart that many astronomers think it may actually be the dwarf galaxy's own nuclear star cluster, the dense knot of stars at its very core, the beating heart of the little galaxy, the center of the thing being eaten. Now here is the delightful part. Here is the part that I love. M54 was catalogued, written down, recorded, given its number, by a French astronomer named Charles Messier. And he did this in 1778. 1778. Stay with me here because the dates matter and I want you to feel the strangeness of them. Charles Messier was a comet hunter. He spent his nights sweeping the sky for comets, and he kept getting fooled by fuzzy little smudges of light that looked like comets but weren't. They never moved. They were just faint, blurry objects fixed in the sky. So, rather sensibly, he made a list of all these fuzzy not comets so that he and others wouldn't keep being tricked by them, a catalogue of the deceptive smudges, and M54, the 54th object on his list, was one of them. He logged it in 1778, a faint blur in the constellation of Sagittarius, just one more fuzzy patch to note and move past. But here is the wonder of it. That fuzzy little smudge he wrote down in 1778 was not part of our galaxy at all. It belonged to another galaxy entirely, the Sagittarius Dwarf. And we did not discover that galaxy until 1994. Do the arithmetic, slowly, the way you might count sheep. Charles Messier catalogued a star cluster belonging to another galaxy in 1778. We didn't even know that galaxy existed until 1994. That's more than 200 years. For over 2 centuries, humans had written down, numbered, studied, and pointed their telescopes at a piece of another galaxy, a whole separate galaxy, without having the faintest idea what they were looking at. We held a fragment of Sagittarius in our hands, in our catalogues, in our books, for 200 years before we understood that the galaxy it came from was even there. There's something almost tender about that, isn't there? A man in the 18th century, by candlelight, carefully writing down a fuzzy smudge so it wouldn't fool him into thinking it was a comet. And all the while, that smudge was the heart of a dying galaxy that the Milky Way was, even then, slowly eating. He could not have known. He had no way to know. And yet there it sits in his catalogue, M54, a tombstone we logged 2 centuries before we knew there was a grave. I want you to hold that thought gently as your eyes get heavy. We are so often looking right at the most extraordinary things in the universe long before we understand them. The truth was there all along. We just hadn't learned how to see it yet. Now, before we drift onward, and we will drift slowly through so much more tonight, I want to plant one more idea in your mind. I'm going to offer it now and return to it later, the way you might set a kettle on to warm while you settle in. Because this slow, gentle, silent meal, this galaxy being eaten right above us, may have given us something. Something close to home. Something close to you, in fact. There's a hypothesis, a leading idea not yet fully settled, so I'll offer it the way it deserves, softly, as a possibility, not a certainty. Some astronomers, notably a researcher named Tomás Ruiz Lara and his colleagues, working in 2020 with the extraordinary data from a spacecraft called Gaia, and we'll come to Gaia later, that patient little star counter, these astronomers have argued something rather wonderful. They've suggested that each time Sagittarius plunges through the disk of the Milky Way, on each of those long, slow passages, the disturbance it causes, the gravitational ripple of a whole galaxy passing through, may have triggered bursts of new star formation in our galaxy. Think of it like a stone dropped into a still pond. The little galaxy plunges through, and the ripples it makes squeeze the gas clouds of the Milky Way, and where gas is squeezed, new stars are born. So every pass of Sagittarius may have sparked a wave of new suns lighting up across our galaxy. And here is the part that I want you to carry into sleep, the part that makes the whole thing feel less like distant astronomy and more like family. Some of those bursts of star formation may have happened right around the time and right around the place that our own sun was being born. Which means, and remember, this is a leading idea, not a settled fact, so hold it lightly. It means our sun, the very star that warms your days and rises over your mornings and gives light to everything you've ever seen, may owe its existence, at least in part, to this slow act of cannibalism. The Milky Way reached out and began to swallow a little galaxy, and in the ripples of that swallowing, a new star kindled into being. And that star may have been ours. We may be here because our galaxy ate another one. I'll come back to that thought later, and we'll sit with it more fully when the time is right. For now, just let it rest at the edge of your mind like a warm coal under the ashes. The sun, you know, the star, at the center of everything you've ever lived through, may exist because of this gentle, silent, ongoing meal taking place above your roof tonight. So let's gather where we are, slowly, before we wander further out into the dark. There is a little galaxy called Sagittarius, 65 to 70,000 light-years away, hidden for so long behind the bright heart of our own galaxy that we only found it in 1994 when 3 astronomers, Ibata, Gilmore, and Irwin, finally noticed it there. And ever since the Milky Way first caught it in its gravity, it has been pulling that little galaxy apart, gently, tidally, stretching its stars into a vast ribbon that now wraps more than 360 degrees around our entire galaxy. It orbits us once every 500 or 700 million years, and on each pass it sheds a little more of itself, so that what remains today is only a stretched, worn remnant of a galaxy that was once far larger. It carries globular clusters into us as it dies, including M54, its own beating heart, a cluster a French comet hunter logged in his notebook in 1778, more than 2 centuries before anyone knew the galaxy it belonged to was even there. And in the slow passing of this little galaxy through our own, new stars may have been born, perhaps even ours. All of it silent, all of it slow, all of it happening right now above the roof over your head in a darkness so vast and so empty that two galaxies can pass straight through each other and almost no two stars ever touch. Let your breathing slow with the pace of it. There is no hurry in any of this. The galaxy above you has been falling into ours for billions of years, and it will keep falling for billions more, and not one moment of it is rushed. It simply happens at its own enormous and patient pace, the way the deepest things always seem to. A tide that takes an eon to come in. A snowfall measured not in minutes, but in ages of the world. And we have only just begun. There is so much more out there in the dark surrounding our galaxy, because Sagittarius is not the only one. It is not the only galaxy our Milky Way has reached for, not the only one being slowly drawn in and unmade. There are others, brighter ones, ones you can see with your own eyes from the right corner of the world. And there are the faint ones, the dim and ghostly ones, so faint you could almost see straight through them. And there are the ones already gone. Galaxies the Milky Way finished eating long ago, leaving behind only long, faint scars of stars threaded through the dark. The fossil traces of meals that ended billions of years before the first human ever looked up. We'll wander toward all of them slowly, one at a time. The bright doomed companions hanging in the southern sky, trailing their long ribbon of stolen gas behind them. The faint dwarf galaxies scattered all around us, some so dark and so quiet they hid from every telescope until just a few years ago. And the ghostly streams of stars that wind through our galaxy's halo like rivers, each one the stretched-out remains of a galaxy that no longer exists, each one a story written in light across the sky above you. But that is all still ahead of us, and there's no need to reach for it yet. For now, just rest where we are. Hold the picture of that little galaxy, Sagittarius, wrapping its stars in a great quiet ring around our own. Hold the thought that we are, all of us, lying here inside a galaxy that is, in the gentlest way imaginable, eating another one. And that somewhere in that slow and silent meal, long before any of us were here, a star may have caught fire. A star that became our sun. There's no need to grasp every detail. You don't have to hold on to the numbers or the names or the dates. If they slip away from you as you drift, that's perfectly all right. The galaxy above you won't mind. It will keep doing what it's doing, slowly and silently, whether you're awake to hear about it or not. The ideas will still be here when you wake. All you need to do right now is breathe and rest, and let the vastness of it hold you the way it's held everything else for billions of years. So settle a little deeper. Let the lamp glow on if you've left it on, or let the dark settle in if you haven't. And let me keep talking softly while our galaxy goes on with its long, quiet meal above us, and we wander a little further out into the dark together. Welcome to the Sleepy Scholar. It's lovely to have you here tonight, wherever you happen to be. Maybe you're tucked under a heavy blanket with the rain on the window. Maybe you're on a long train, watching the dark slide past. Wherever you are, and whatever time it reads on your clock, settle in. You've found the right place to be still for a while. And if you enjoy these slow journeys into the strange and beautiful corners of the universe, a quiet like and subscribe really does help this Sleepy Little Scholar's channel keep going. Small creators like me rely on it more than you'd think. To those of you already here, already part of this, thank you truly. Now I'm curious, and you can tell me before you drift off if you like. Where in the world are you listening from tonight? Leave it in a comment. I love imagining all the dark windows scattered across the globe with these same gentle stars overhead. So, let's go back to the beginning of this particular story. The galaxy our own is quietly devouring, even now. Because for most of human history, nobody knew it was there at all. It was only in 1994 that three astronomers, Rodrigo Ibata, Gerard Gilmore, and Mike Irwin, first realized they were looking at an entire galaxy hidden in plain sight. It's called the Sagittarius Dwarf Spheroidal Galaxy, and the reason it stayed hidden for so long is rather lovely in its way. It was tucked on the far side of our galaxy's center, behind the thickest, most crowded star fields of the Milky Way's heart. Imagine trying to spot a single small lantern carried behind a great bonfire. The bonfire's light drowns it. For all those centuries, the bright, busy glow of our own galactic center simply washed it out. And so this whole other galaxy sat there, quietly, just waiting to be noticed. And when they finally noticed it, they noticed something else too. It was being torn apart. Now, I want to be careful with that phrase because it sounds violent, and this is not a violent story. Sagittarius isn't being shattered or smashed, it's being stretched. The Milky Way's gravity simply pulls a little harder on the near side of that little galaxy than it does on the far side, and over an unimaginable stretch of time, that gentle difference slowly draws its stars out into long, trailing ribbons. Not a crash, not an explosion, just a slow, patient unraveling, the way a thread might be teased loose from the edge of a sweater, one fiber at a time. And here's the part that I find quietly astonishing, the kind of thing worth carrying into a dream. The debris from all that unraveling, the stars peeled away from Sagittarius over the ages, forms something called the Sagittarius Stream. And this stream of stolen stars doesn't just drift off in one direction, it wraps, it loops all the way around, more than 360 degrees completely encircling the entire Milky Way. One small, doomed galaxy, its remains drawn out into a great ring, threaded right around our own. It's one of the largest single structures of star debris we know of anywhere in our galaxy. A ribbon of one galaxy's dead wound gently around the whole body of another. This doesn't happen in a moment, of course. Sagittarius takes its time. It swings around the Milky Way in a long, looping orbit that takes somewhere between roughly 550 and 750 million years to complete, just one trip. And it has very likely made this journey several times already, around and around. And on each pass, the Milky Way's pull takes a little more of it. A few more stars peeled away. A little more of its body given up to the ring. What began, the models suggest, as a far larger and more substantial galaxy has been slowly whittled down pass after pass after pass into the stretched and distorted remnant we see today. A galaxy being eaten not in a single bite, but in patient, gentle lapse over billions of years. And while all of this was unfolding in the dark, something rather charming was happening down here, far below, long before anyone understood any of it. Back in 1778, think of that, more than 2 centuries ago, by candlelight and brass telescope, a French comet hunter named Charles Messier was carefully cataloguing all the faint, fuzzy smudges in the sky that kept fooling him into thinking they were comets. He gave each one a number so he and others wouldn't be tricked again. And one of the objects he wrote down, one he called M54, was a dense little ball of stars, a globular cluster sitting quietly in the constellation of Sagittarius. What Messier could not possibly have known, what nobody would know for another 216 years, is that M54 doesn't actually belong to our galaxy at all. It sits right at the heart of the Sagittarius dwarf. It may even be its very core, its bright nuclear cluster, the dense center of that other galaxy. So when Messier jotted down that little number by his candle in 1778, he was, without the faintest idea of it, recording a piece of another galaxy. He catalogued a fragment of Sagittarius 2 full centuries before anyone realized that Sagittarius was even there. The clue had been sitting in his notebook all along, waiting patiently for the rest of us to catch up. And there's one more thread I want to lay gently in your hands before we drift any further. One we'll return to later, so don't feel you need to hold it tightly. Just let it rest there. Some astronomers, and this is a leading idea rather than a settled fact, so hold it loosely, some astronomers now think that those repeated passages of Sagittarius through the disk of our galaxy may have done more than just give up stars. Each time that little galaxy plunged through the Milky Way, it may have stirred and squeezed the gas it passed through, and squeezed gas is exactly how new stars are born. So those great slow dives may have triggered bursts of star formation across our galaxy, possibly, just possibly, including stars that formed around the time our own sun first caught fire. I'll say that again, softly, because it's worth carrying down into sleep. The sun you've lived your whole life beneath may owe its very existence, in some small part, to this. To one galaxy, quietly being eaten by another billions of years ago, in the silent dark overhead. We'll come back to that, there's no rush at all. So let us move now to something you can actually see if you happen to be lying somewhere in the southern hemisphere tonight, or if you've ever looked up at a dark sky south of the equator and noticed something unexpected. 2 soft patches of light. Not stars exactly, not clouds, something else entirely. They look at first glance like someone tore off 2 small pieces of the Milky Way and set them adrift. And in a sense, that is exactly what is happening to them slowly, over billions of years, though they don't know it yet. These are the Magellanic Clouds, the Large Magellanic Cloud and the Small Magellanic Cloud, and they are the brightest satellite galaxies the Milky Way has. Actual galaxies, entire systems of stars and gas and dust, visible to the naked eye, hanging there in the southern sky like 2 companions who have wandered a little too close to something much larger than themselves. The Large Magellanic Cloud sits roughly 160,000 light-years from us. The Small Magellanic Cloud a little farther, around 200,000 light-years out. To put that in terms your sleepy mind can rest against for a moment. The light reaching your eye from those soft patches left those galaxies long before our species existed, before we had language or fire or any memory of anything at all. The light you would see from them tonight is 160,000 years old, and yet there they are, close enough on cosmic scales to be called our nearest bright neighbors. Now, they carry a name that is both accurate and a little unfair. Ferdinand Magellan. You may know that name. The Portuguese explorer whose expedition set out in 1519 and after extraordinary hardship and loss completed the first circumnavigation of the Earth in 1522. When his ship sailed into the deep southern seas away from the latitudes that European navigators usually kept, his crew looked up and saw these 2 pale patches in the sky, and they recorded them. The clouds entered European charts and records, and eventually, over the following centuries, the name stuck. The Magellanic Clouds, named for a man from Portugal who sailed south and looked up. But this is where the name becomes a little unfair, because Magellan's crew were not the first to see them, not even close. They were simply the first to carry the observation back to European cartographers in a form that got preserved and widely distributed. In the 10th century, the Arab astronomer Abd al-Rahman al-Sufi, known in the West as Azofi, wrote about these clouds. He called them the White Ox, al-Bakr, and noted them in his famous book of fixed stars, a meticulous survey of the sky that shaped Islamic and European astronomy for centuries. Al-Sufi knew about those clouds 500 years before Magellan's voyage. They were part of the sky he mapped and named and thought about carefully. And before Al-Sufi, before any of this written record, there were Aboriginal Australians who have lived beneath the southern sky for tens of thousands of years. The Magellanic Clouds appear in their astronomical traditions and their stories, carrying meaning, carrying knowledge, part of one of the oldest continuous sky-watching traditions on Earth. The clouds we now call Magellanic were watched and known and named in ways that predate any written account by an enormous stretch of time. So when we say Magellanic Clouds, it is worth knowing that you are using the name of the relative newcomer to the story. But whatever we call them, they are extraordinary. Let us sit with them for a little while. The Large Magellanic Cloud, which you might see abbreviate to LMC in any astronomy text, is not a neat, organized spiral like our galaxy. It is irregular, slightly chaotic, as though it has been nudged and pulled a little out of shape, which, as we are about to discover, is exactly what has been happening to it. It contains hundreds of millions of stars, enormous clouds of gas where new stars are still being born, and structures of extraordinary beauty and scale. It is, in its own right, a rich and complex galaxy. The Small Magellanic Cloud, the SMC, is smaller and more ragged still. It is closer to a shapeless puff of stars than anything you might draw in a diagram labeled Galaxy. But it too contains tens of millions of stars and gas, and the quiet ongoing processes of stellar life and death. Together they drift through the space around our galaxy, and they are not drifting quietly, because trailing behind them, pulled from them by the gravity of the Milky Way and by their own motion, is one of the largest structures in our cosmic neighborhood. Something you would never see with your naked eye because it is made of hydrogen gas rather than light. But if you could somehow see radio wavelengths, if your eyes were tuned to that part of the spectrum the way a radio telescope is, you would look up at the sky and see it stretching away from the clouds in an enormous ribbon, sweeping across more than 100 degrees of sky. More than half the visible celestial sphere, end to end. This is the Magellanic Stream, 100 degrees, think of that. If you held your arm straight out and slowly swept it from one horizon to the other, you would trace about 180 degrees. The Magellanic Stream covers more than half of that sweep. It is, in plain terms, enormous, and it is not empty. The Magellanic Stream contains roughly 1 billion solar masses of gas. 1 billion times the mass of our Sun, all of it hydrogen, all of it strung out in this vast, trailing ribbon behind the clouds as they move. That gas was once inside those galaxies. It was the raw material from which future stars might have been born inside the LMC and the SMC. But it was pulled free. And now it trails behind. Pulled how? This is where it becomes interesting and a little bit contested in the gentle way that good science is sometimes contested. The dominant picture is tidal stripping, the same basic process we talked about with Sagittarius. The near side pulled more strongly than the far side, the galaxy stretched and losing material from its edges, the Milky Way's gravity reaching out over 100,000 light-years and slowly, steadily taking. But there is another force at work too. The Milky Way is not just a disk of stars, it is also surrounded by an enormous diffuse halo of very hot gas, hot enough to be a plasma. And as the Magellanic Clouds move through that halo, the gas pushes back against them, the way water pushes against a swimmer moving through it. And if you have ever tried swimming with loose clothing on, you may have a sense of what happens next. The clothing catches the water and pulls backward. Ram pressure stripping, astronomers call it. The hot halo gas strips the cloud's own cooler gas away, not by pulling, but by pushing, pressing it back and peeling it away. The honest answer is that both processes are likely at work, the tidal pull and the ram pressure together, and separating which stripped which gas and when is still an active area of work. The Magellanic Stream is real and enormous and measured. Exactly how it formed involves ongoing refinement. And there is more. The stream trails behind the clouds, yes, but in front of them, rushing ahead of their direction of travel, there is another structure, the leading arm, gas that has been pulled forward out ahead of the cloud's motion. So the clouds have a tail and an arm, debris behind them and debris in front, like a comet pulled in both directions at once, material both falling behind and racing ahead, depending on the dynamics of the orbit. It is a strange and beautiful asymmetry. The Eton and the Eta both leaving marks ahead of and behind the motion, and then between the two clouds themselves, between the large and the small, there is the Magellanic Bridge, a stream of gas and some stars connecting the LMC and the SMC directly to each other. Evidence that these two galaxies have not merely been passive neighbors sitting side by side. They have interacted, they have tugged at each other. The bridge is a scar of that gravitational conversation between them, two galaxies who have been bumping and pulling at each other, even as something far larger pulls at them both. This brings us to something rather poignant about the small Magellanic Cloud specifically. It is the smaller of the two, as the names suggest, and it finds itself caught between two gravitational presences larger than itself. On one side, the Milky Way, vast and patient, reaching in with tides. On the other, the large Magellanic Cloud, its companion, much more massive than it, tugging with its own gravity. Some astronomers think the SMC may be in the early stages of being torn apart, not just by the Milky Way, but by the combined gravity of both its larger neighbors at once. A small galaxy caught in a tug of war, pulled from two directions, neither captor willing to yield. It is a quiet situation, slow by any human measure, but a situation nonetheless. Now, let me share something that was not obvious for a long time and that changes the entire picture of how we think about the clouds. For many years, the assumption was simple enough. The Magellanic Clouds have been orbiting the Milky Way for billions of years, going round and round in long, slow loops, the way the moon goes around the Earth. Long-bound companions, a relationship as old as the galaxy itself. But when astronomers began measuring the actual velocities of the clouds with great precision, how fast they are truly moving, and in what direction, the numbers came out surprisingly large. The clouds are moving very fast relative to the Milky Way. Fast enough that some models suggest they may not be on long settled orbits at all. Fast enough that they may only recently have been captured by the Milky Way's gravity and may in fact be on their very first close passage. This idea is associated particularly with the work of Gurtina Besler and Nitya Kalivayalil and their collaborators. The hypothesis, which remains an active area of debate and research, is that the Magellanic Clouds were out in the wider universe for most of cosmic history and have only recently, on astronomical timescales, fallen into the Milky Way's gravitational embrace. Possibly, this is their first visit, the first time they have come this close, which would mean the Magellanic Stream, the leading arm, all of that material pulled from them, all of it the product of this first encounter, the first time the Milky Way has reached out and begun to take from them. It is a strange thought to carry. These two bright patches in the southern sky, companions so familiar they have names in dozens of human traditions across millennia, may be strangers. Visitors on their first approach, not old friends of the Milky Way, but newcomers falling inward, seeing all of this for the first time. And one reason astronomers take this seriously is the mass of the large Magellanic Cloud, because the LMC is not negligible. It is surprisingly massive, and massive enough, in fact, that it does something rather remarkable. It gravitationally perturbs the Milky Way, not by a tiny amount, Measurements suggest that the LMC is massive enough that it is tugging on the outer halo of the Milky Way, the diffuse cloud of stars and dark matter that surrounds our galaxy, and actually pulling it, shifting its distribution. The outer halo of the Milky Way is slightly lopsided, slightly pulled in the direction of the LMC because the LMC is heavy enough to do that. Some models suggest it is even slightly shifting the Milky Way's center of mass, displacing the whole galaxy's gravitational heart by a small but measurable amount. So, who is eating whom? The Milky Way is, in the long run, almost certainly going to win this gravitational encounter. The clouds are destined to be pulled apart and absorbed, but right now, in this moment of the encounter, the LMC is pushing back. It is pulling on us. Two objects influencing each other, one far larger and one destined to lose, but both of them, for now, in a real gravitational conversation. Let that sit for a moment. The Milky Way is eating the Magellanic Clouds, and the Magellanic Clouds are just slightly shaking the Milky Way while it does so. Inside the large Magellanic Cloud, there is something that deserves its own quiet moment of attention, a region that if you could somehow stand nearby and look at it would stop you completely, because the large Magellanic Cloud contains the most vigorous, most active, most productive star-forming region in the entire local group. Not just in itself, but in the Milky Way's neighborhood, the whole collection of galaxies we live among. It is called the Tarantula Nebula, sometimes written as 30 Doradus, its designation in star catalogues. A nebula is simply a cloud of gas and dust, the nurseries where stars are born. And the Tarantula Nebula is one on a scale that has no equal anywhere nearby. It spans roughly 1,000 light-years across. It contains millions of newly formed and forming stars. Its filaments of glowing gas and its dark channels of shadow do look, in images, something like the legs of a great spider. Hence the name. But the name undersells the scale of it. If the Tarantula Nebula were as close to us as the Orion Nebula, the nearest comparable structure in our own galaxy, it would be bright enough to cast shadows on the ground at night. It would be the most dramatic object in our sky. Instead, it sits 160,000 light-years away, tucked inside a neighboring galaxy, visible only as a bright knot of light within the soft glow of the LMC. Nothing like it exists in the Milky Way right now. Our galaxy has star-forming regions, yes, but nothing of that scale, nothing with that density of young massive stars. In this sense, looking at the large Magellanic Cloud, we are looking at something our galaxy once did and may no longer be capable of doing in the same way. The LMC is doing it now, blazing with new stellar life, even as the Milky Way reaches out and slowly, gently, begins to take it apart. And it was within the large Magellanic Cloud that in 1987 something happened that remains one of the most remarkable events in modern astronomy. A star exploded. This is not unusual in cosmic terms. Stars explode all the time across the universe. But this particular explosion happened close enough for us to detect it with instruments on Earth. A star in the Tarantula Nebula reached the end of its life and detonated as a supernova. Supernova 1987A it was called, catalogued by the year of its discovery. The closest observed supernova in about 400 years, since astronomers last had such a nearby stellar death to study. What made the detection extraordinary, but one of the things that made it extraordinary, was not the light. The light was visible eventually, and astronomers all over the southern hemisphere turned their telescopes toward it and watched. But before the light arrived, before any telescope confirmed the event optically, detectors buried underground in different parts of the world, detectors designed to catch the nearly uncatchable, picked up something else. A brief burst of neutrinos, subatomic particles so small, so nearly massless, so reluctant to interact with ordinary matter that they pass through the entire Earth as though the Earth is barely there at all, as though it is made of smoke. But a supernova produces them in such extraordinary numbers that even with their near-complete refusal to interact with anything, a few dozen of them bumped into the detector's atoms in a way that left a signal, registered, noted, a momentary flutter of ancient particles in instruments deep underground, and then the light followed. The neutrinos arrived slightly before the light, which is itself a story about how supernovae work. The core collapse happens first, the neutrinos flood out in the first instant, and then the shockwave works its way through the star and finally blasts off the outer layers, producing the burst of light that we see. So the neutrinos came first, a whisper before the shout. And those detectors buried in mines and tunnels and water tanks caught that whisper from 160,000 light-years away. It is one of the details of modern astronomy that if you let yourself feel it rather than just note it, is genuinely astonishing. A star died in another galaxy, and we felt it. Supernova 1987A and the Tarantula Nebula exist inside the large Magellanic Cloud, a galaxy that is right now being slowly pulled apart and absorbed by ours. The most vigorous star nursery in our neighborhood and the most studied supernova in modern astronomy. Both of them in something the Milky Way is eating. When the LMC is finally gone, dispersed into streams and halo stars over billions of years, all of that will have become part of us. The gas that is still falling from the Magellanic Stream may eventually rain down into our galaxy and kindle new stars, the eaten galaxy's fuel becoming tomorrow's suns. The Tarantula Nebula stars will end up scattered into our halo. Even the memory of supernova 1987A will belong, in some distant sense, to a galaxy that has absorbed the one it happened in. There is something very quiet in that, something that takes a moment to settle. And the Magellanic Clouds did not arrive alone. This is something that has only become apparent as surveys have grown sensitive enough to see the very faintest objects in the sky around those companion galaxies. The Magellanic Clouds are large enough, massive enough, that they have their own satellites. Small dwarf galaxies, very faint, orbiting the LMC and the SMC the way the clouds orbit the Milky Way. And when the clouds fell into the Milky Way's gravitational reach, they brought those smaller companions with them. The whole group fell in together. So when astronomers began finding new, faint dwarf galaxies clustered suspiciously close to the position of the Magellanic Clouds in the sky, they started to suspect that some of these were not independent Milky Way satellites at all. They were the clouds' satellites, galaxies that orbit a galaxy. A small galaxy with its own smaller galaxies, all of them now falling toward the Milky Way together, all of them bound for the same long, slow fate. It is a little like discovering that a visitor who came to your door brought their whole family with them, and all of them, in the long run, are going to become part of your household. The survey work that found these companions came from instruments designed to look at enormous areas of sky very deeply, patiently, looking for the faintest concentrations of stars. The Dark Energy Survey in particular, which we will return to in a little while, discovered a cluster of new, faint dwarf galaxies concentrated near the Magellanic Clouds in a way that was not random, not coincidental. They were arranged around the clouds the way satellites arrange themselves around a planet. And that clustering told a story. These were not separate arrivals, they were part of the same incoming group. So the cannibalism is layered. The Milky Way is eating the Magellanic Clouds. The Magellanic Clouds are, in a sense, also contributing smaller galaxies they themselves brought along. And all of it is folding slowly over billions of years into the body of our galaxy, which has done this before and will do it again. It is worth pausing here, just for a breath, to hold the whole picture we have assembled so far, because it is a large one. There is the Sagittarius Dwarf on the other side of the galaxy from us, being pulled apart on each of its long, slow orbits, shedding stars into a stream that wraps completely around the Milky Way. A stream so vast that you could, in principle, be standing inside the debris of a dying galaxy right now and not know it. There is M54, catalogued by a French astronomer with a candle 2 centuries ago, sitting at the heart of Sagittarius without anyone yet knowing it was part of another galaxy at all. There is the possible echo of Sagittarius's passages in the stars around us, and the softest possible thread suggesting even the sun's birth may have been touched by this. And now, stretching away in the southern sky, there are the Magellanic Clouds, the large at 160,000 light-years, the small at 200,000. Visible to human eyes across cultures and centuries, known to Arab astronomers in the 10th century, and to Aboriginal Australians for far longer. Trailing behind them an enormous ribbon of gas, 1 billion solar masses of hydrogen, the Magellanic Stream spanning more than 100 degrees of sky, and a leading arm ahead of them, and a bridge between them, and their own smaller satellite galaxies tumbling along behind. All of it in motion, all of it falling slowly toward us. And inside the large cloud, the brightest star-forming region in our neighborhood, the Tarantula Nebula, blazing with stellar birth, and in 1987 a star that died there and sent its neutrinos through the Earth before its light arrived. The Milky Way is eating, and what it is eating is beautiful. We are not done with the ways the sky tells this story. There is still the evidence written in the streams of stars that tell the tale of galaxies already fully consumed, already gone, their bodies dissolved into ribbons of shared motion threading through the halo above us. The work of the Gaia spacecraft and its 2 billion stars, each measured and positioned with extraordinary precision, waiting to be read like a palimpsest of the galaxy's past. The ancient merger that shaped the Milky Way we live in. The ultra-faint dwarves so close to transparent they are barely galaxies at all. The coming surveys that will reveal how many more meals are still hidden. But all of that waits for us a little further along. For now, let the southern sky rest in your mind. 2 soft patches of light traveling together, trailing gas across half the sky, bringing their own companions, visited and watched and named by humans long before we understood what they were. 2 galaxies that the Milky Way has begun to take apart, slowly, silently, as it has taken apart so many others before. No rush, there is no rush at all. The gas in the Magellanic Stream has a long way still to fall before it reaches us. The clouds themselves will orbit for millions of years more before the tides begin to win in earnest. The sky tonight looks exactly as it did last night, and will look exactly the same tomorrow and for 10,000 nights after that. Nothing you can see is moving. The cannibalism is real, but it is ancient, and it is slow, and it is, in its strange way, deeply, profoundly calm. Wherever you are right now, if you can see the southern sky, those 2 pale patches are there. And now you know something of what they are, and what is happening to them, and why the Milky Way is reaching out toward them the way it reaches out toward everything that comes close enough. And if you drift off here, that is perfectly fine. The clouds will still be there when you wake. They have been there for billions of years. They are not going anywhere, not quickly. And the story continues, quietly, overhead. And now, let us turn, gently, without hurry, toward the brighter of those 2 soft companions. Because the large Magellanic Cloud deserves a moment of its own. Not as a footnote, not as a curiosity, but as a place. The large Magellanic Cloud sits about 160,000 light-years away. The small Magellanic Cloud a little further, around 200,000. both visible to the naked eye from the southern hemisphere on any clear night, not as points of light the way stars are points, but as soft, detached patches, as if someone had torn a small piece from the Milky Way and set it slightly to the side, which, in a sense, is almost exactly what has happened, only in reverse. For most of human history, they were simply there, part of the sky, named and watched and incorporated into the stories of the sky-watching peoples of the Southern Hemisphere long before European astronomy took notice. Aboriginal Australians held detailed knowledge of them. Polynesian navigators used them. The 10th century Persian astronomer al-Sufi noted them in his Book of Fixed Stars, that careful and meticulous catalogue of what the sky actually contained rather than what it was supposed to contain. They were, for millennium after millennium, simply features of the night. Then came Ferdinand Magellan, or more precisely, came Magellan's 1519 to 1522 circumnavigation, during which European sailors crossing the southern hemisphere recorded those patches and brought the observation back to audiences who had never seen them. The clouds carry his name now in the way that explorers so often have their names attached to things they were far from the first to find. It is one of astronomy's small and recurring ironies. The sky belongs to everyone who looks at it. What those observers, all of them, from ancient Australia to medieval Persia to Renaissance Portugal, could not have known was what the clouds actually are: separate galaxies. Companions of the Milky Way, or perhaps something stranger than companions, something more like travelers, only recently arrived. Because here is where things become genuinely surprising, and genuinely uncertain, and genuinely beautiful all at once. The prevailing hypothesis about the Magellanic Clouds, developed most fully by Gertina Besler, Nitya Kalivayalil, and their collaborators, is that the clouds may be on their first passage close to the Milky Way. Not long-bound satellites that have been circling us for billions of years, new arrivals, recent captures on an enormous looping approach that has only now brought them into the range where our galaxy's gravity begins to matter. The evidence for this is in their speed. When astronomers measured the proper motion of the Magellanic Clouds, their actual movement across the sky, a painstaking measurement, the velocities came back unexpectedly high. The clouds are moving fast, perhaps too fast to have been in a stable orbit around the Milky Way for billions of years. They may have come from further away. They may have been their own system, the large cloud and the small cloud orbiting each other in their own small dance, falling together as a pair toward a galaxy that will eventually, inevitably, take them apart. If that is true, and it remains an active debate, the kind that astronomers write careful, precisely worded papers about, then the Magellanic Clouds are not old prisoners. They are recent visitors standing in the doorway, still wearing their traveling clothes, still trailing the gas of their journey behind them. And that gas is something worth pausing on. Stretching behind the clouds across more than 100 degrees of sky, more than half the visible sky, if you could see it, runs the Magellanic Stream, a ribbon, or rather a vast and tenuous river of hydrogen gas. About 1 billion solar masses of it, 1 billion times the mass of our Sun, drawn out across the sky in a trail that follows the clouds the way a comet's tail follows the comet, pointing back along the direction of travel. Ahead of the clouds there is a separate structure, the leading arm, gas pulled forward by the combined gravitational tugging of the Milky Way and the clouds themselves flung ahead in the direction of motion. And between the large cloud and the small, connecting them like a thin bridge between two islands, runs the Magellanic Bridge. Gas and some stars strung between the two, evidence that the clouds have been pulling at each other as well, not just being pulled at by us. The origin of the stream itself is still being worked out. Tidal forces, the gravitational stretching that pulls the near side harder than the far, almost certainly play a role. But ram pressure stripping may contribute too. As the clouds move through the Milky Way's own extended halo of hot gas, that halo pushes back, peeling gas away from the clouds the way rushing water pulls loose fabric from a swimmer. Likely, both processes are at work together, each contributing its portion to that enormous trail. What becomes of all that gas eventually? It falls. Slowly over timescales that make slow seem like an understatement. Eventually, much of the Magellanic Stream's hydrogen will rain down onto the Milky Way, and hydrogen is the raw material of stars. The gas stripped from the clouds, the traveling gift of these doomed companions, may one day fuel new stars inside our own galaxy, the substance of the Magellanic Clouds becoming the substance of new suns. It is a transformation so gradual and so complete that the word cannibalism, which is how astronomers sometimes describe it, starts to feel almost too dramatic. It is more like inheritance, a slow and impersonal passing of material from one form to another. Now, the large Magellanic Cloud is not simply a reservoir of gas waiting to be dispersed. It is, right now, the most vigorous star-forming region in the entire local group of galaxies. Not anywhere in the Milky Way, not in Andromeda. In the large Magellanic Cloud. The place responsible for this is the Tarantula Nebula, also catalogued as 30 Doradus, a stellar nursery so large, so bright, so relentlessly productive that if it were located where the Orion Nebula sits, the great nebula in Orion's sword, that soft smudge visible to the naked eye, it would cast visible shadows on Earth at night. It would be bright enough to read by. It is 160,000 light-years away, and it is still extraordinary. A cauldron of gas and young stars and radiation, all of it churning. The Milky Way has nothing quite like it. Whatever is happening inside the large Magellanic Cloud, the tidal interactions with the Milky Way, the close relationship with the small cloud, the complex history of their approach, it has produced something remarkable, the most active stellar nursery we can see. And then there is supernova 1987A. On the 23rd of February 1987, a star in the large Magellanic Cloud exploded. It had been a blue supergiant, a massive star burning fast and hot and brief, and when it reached the end of what such stars reach the end of, it collapsed and then detonated in a supernova, the closest observed supernova in roughly 400 years. Before the light of the explosion reached us, before astronomers looked up and noticed the new brightness in the Tarantula Nebula, a burst of neutrinos arrived. Neutrinos are extraordinarily reluctant to interact with anything. They pass through matter as if matter is almost not there at all. A beam of neutrinos can pass through a light-year of solid lead and emerge mostly unimpeded on the other side. And yet 3 separate neutrino detectors on Earth, in Japan and in the United States and in the Soviet Union, registered a brief burst of them on that February morning, fewer than 24 neutrino interactions in total across all 3 detectors, in a window of about 13 seconds. But those few interactions told a story. They confirmed what theoretical models had predicted, that a core collapse supernova releases the vast majority of its energy not as light, not as the dramatic visible explosion, but as a flood of neutrinos gone almost before they can be measured. The light arrived hours later, the neutrinos came first. It remains one of the most remarkable moments in the history of observational astronomy. And it happened not in our galaxy, but in one of these soft, southern patches, in the large Magellanic Cloud, in the companion that is slowly being pulled apart. And the small Magellanic Cloud, meanwhile, is caught between forces. The large cloud is bigger, more massive, and the two have been interacting. The Magellanic Bridge, that thin stream of gas between them, is the visible evidence of the large cloud's pull on the small, and the Milky Way pulls at both of them. The small cloud may itself be in the early stages of disruption, caught in a gravitational negotiation between 2 larger bodies, neither of which is going to let it simply pass through unchanged. In fact, scattered around the Magellanic Clouds, close to them in the sky and likely close to them in space, are a number of very faint, very small dwarf galaxies, newly discovered, still being characterized. Some astronomers believe these small dwarfs arrived with the clouds, not independently captured by the Milky Way, but companions of the clouds themselves, satellites of a satellite, a small retinue traveling with the two clouds on their long approach. A galaxy with its own smaller galaxies all falling together now into the gravitational territory of ours. The Milky Way did not just gain two companions, it may have gained an entire small entourage, and then there are the ones that are already gone. Not gone in the sense of vanished without a trace. Gone in the way that a river is gone after it has been braided into the sea. The water is still there, still present, still real, but it no longer has a shape you would call a river. It has become part of something else. It has become the sea itself. This is what the Milky Way has been doing quietly for billions of years. Not just to the Sagittarius Dwarf, which is still in the process of being unraveled, not just to the Magellanic Clouds, which still hold their shape against the southern sky, but to galaxies that came before them. Galaxies that arrived, were stretched, were pulled apart, and then were absorbed so completely that no body remained. Only trails, only threads, only the faintest structural echoes preserved in the motions of stars. And for a very long time, we could not read those echoes. The stars were just there, orbiting, scattered through the halo, and we had no way of knowing which ones had always been ours and which ones had been borrowed, taken, consumed from somewhere else. But that changed. A stellar stream is, in its simplest description, the ghost of a galaxy, or the ghost of a globular cluster. When a small object, a dwarf galaxy or a dense ball of stars, orbits the Milky Way close enough and long enough, the tidal forces begin to work on it. The near side of the object is pulled a little harder than the far side. The object is not rigid. It cannot simply accelerate as a whole, so it stretches. Stars on the leading edge drift ahead, pulled just slightly faster along the orbit. Stars on the trailing edge fall behind, pulled just slightly slower. Over millions of years, these drifting stars form two long trails, one reaching ahead of the object, one streaming behind, like a comet's tail, except that both tails go in opposite directions along the orbit, and the comet itself is made of stars. What you are left with, eventually, is a ribbon. A long, thin, curving ribbon of stars following a shared path through the halo, the scattered remains of something that used to be a coherent, bounded object. The stars in the ribbon are not falling toward each other. They are not clustering. They are simply traveling together, spread out along the same ancient orbital track, carrying in their individual motions and their individual chemistries the shared memory of the object they once belonged to. This is the key thing. The stars in a stream share two things that stars born separately in the Milky Way's halo do not share. They share a common motion. They are moving through space along similar trajectories because they were all once part of the same orbiting body. And they share a common chemistry. The particular mix of elements in their atmospheres reflects the conditions in the galaxy or cluster where they formed, which was a different environment from the Milky Way's main disk or bulge. These two facts together, shared motion, shared chemistry, are what allow astronomers to identify a stream at all, to separate its member stars from the general background of halo stars that were born here, and to say with confidence, these stars are not from here. They came from somewhere else. For a very long time, this work was extraordinarily difficult. The halo is vast, the streams are thin, and the stars are scattered across enormous volumes of space, separated by light years, with no labels. To find a stream in the old data was like trying to identify a river by sampling random tablespoons of ocean water and noticing that a few of them taste slightly different. Possible in principle, extraordinarily patient in practice. And then Gaia arrived. The Gaia spacecraft was launched by the European Space Agency in 2013, and what it set out to do was something almost absurdly ambitious: measure the positions, distances, motions, and brightnesses of nearly 2 billion stars. Not to a rough approximation, but with a precision that had never been approached before. The distances accurate to within tiny fractions of a percent for nearby stars. The motions measured not just across the sky, but, for many stars, in 3 dimensions, including the radial velocity, how fast the star is moving toward or away from us, so that the full 3-dimensional trajectory through space could be mapped. Nearly 2 billion stars, each one a point of light that had previously been a number in a catalogue, a dot in a survey image, a smear of photons on a photographic plate. Gaia gave each of them a precise address in the galaxy, a velocity vector, and a place in the great architecture of the Milky Way's structure. When astronomers began working through that data, what they found was extraordinary. The halo, which had looked in coarser surveys like a more or less smooth cloud of stars orbiting the galactic center, was not smooth at all. It was threaded, laced through with structure. Dozens of streams, ribbons, overdensities, shells of stars that shared orbits and motions and did not belong to the general background. The halo was not a formless cloud. It was a palimpsest, a surface written on and written on again, and written on again, each inscription the ghost of a different galaxy, partially overlapping, partially distinct, waiting for an instrument precise enough to read it. The field has a name for what Gaia made possible. It is called galactic archaeology. The analogy is deliberate and apt. An archaeologist does not need to have been present at the city to know the city was there. They dig into the present-day Earth and find the layers, the pottery, the walls, the ash, the bones, and from those layers they reconstruct what existed before. A galactic archaeologist does the same thing with stars. They do not need to have watched the ancient mergers happen in real time. They sift through the present-day positions and motions of billions of stars, and from the patterns they find, they reconstruct what existed before. Which galaxies arrived when? Which ones are still in the process of being digested? Which ones are so old and so thoroughly mixed that only the faintest chemical traces remain? The chemical traces are, in fact, one of the most powerful tools available. Stars form from gas. The gas carries whatever elements were present in the local interstellar medium at the time of formation. Hydrogen and helium, certainly, but also heavier elements in ratios that depend on which generations of previous stars had already lived and died in that region. A galaxy that formed few stars will have a different chemical fingerprint than a galaxy that formed many. A galaxy that was quenched early will carry a different ratio of, say, iron to magnesium than one that kept forming stars for billions of years. These ratios are baked into the stars at birth, and stars preserve them across their lifetimes. So a star that formed in a dwarf galaxy that was eaten by the Milky Way 5 billion years ago still carries, in its atmosphere today, the particular chemistry of that dwarf galaxy. It is chemically tagged, not by us, but by the conditions of its birth. We simply have to learn to read the tag, and with spectroscopic surveys increasingly paired with Gaia's astrometry, its precise positional measurements, that reading has become possible at industrial scale. You can now take a sample of tens of thousands of halo stars, measure their orbital properties, measure their elemental abundances, and cluster them in that multi-dimensional space. Stars that cluster together in both orbit and chemistry are very likely from the same progenitor. You are not seeing the galaxy anymore. You are seeing its fossils arranged by family resemblance, Let's talk about some specific streams because the names and the details are worth sitting with. The GD1 stream is one of the longest, thinnest, most precisely mapped of what are called cold stellar streams. Cold here does not mean temperature in the everyday sense. It means that the stars in the stream are moving in very close lockstep. Their velocities are tightly clustered, not widely spread. This coldness, this tight coherence of motion, is a sign that the stream came from a small progenitor, probably a globular cluster rather than a full dwarf galaxy, because a larger object would have had more internal velocity spread, and that spread would be preserved in the stream, making it broader, fuzzier, hotter. GD1 is pencil-thin, stretching across a large arc of sky, the dissolved remains of a cluster that once orbited the Milky Way and over time was simply pulled apart, star by star, into this long, cold ribbon. But GD1 has something else. It has gaps, not everywhere. But there are places along the stream where the density of stars drops where you would expect stars to be based on the stream's overall arc, but they are not there. And alongside one of the gaps there is a feature called a spur, a short branch of stars veering off to one side as if something came through the stream and knocked a portion of it sideways. What could make a gap in a stellar stream? One possibility is that a dense, compact object passed through the stream, something massive enough to gravitationally scatter the stars apart, to carve a hole and leave a spur. A giant molecular cloud could do this, a particularly dense clump of stars could do this. But some astronomers have raised the possibility that the gap maker was neither of those things, that it was a clump of dark matter, a concentration of the invisible mass that makes up most of the Milky Way's halo, passing through the stream like a bullet through a curtain, leaving a tear. If that interpretation is correct, then GD1 is not just the ghost of a dissolved cluster, it is also a detector, a long sensitive wire stretched across the halo, recording the passage of objects we cannot see. The stream is reading the dark matter distribution. It is writing the dark matter's signature into the places where stars are missing. This is the kind of thought you can carry gently with you as you fall asleep. The idea that the scars of cannibalism are themselves instruments of measurement. The streams are not just evidence of what happened, they are tools for learning what is there, still invisible, still shaping everything. The Helmi Streams are older, and the story of their discovery is worth pausing on. In 1999, the astronomer Amina Helmi and her collaborators were working with a much smaller data set than Gaia would eventually provide, a few thousand halo stars with precisely measured motions. Within that sample, they noticed a group of stars that clustered in a particular way in velocity space. Not in position, and the stars were scattered across different parts of the sky, different distances, not obviously associated with each other at all. But in the way they were moving, they shared something. They were not random. They formed a coherent group in the mathematical space that describes orbits. And the implication was clear. These stars had once been part of the same object, a dwarf galaxy that had been accreted into the Milky Way billions of years earlier, its body long since stripped and scattered, its stars now spread across the halo but still moving, still carrying in their velocities the memory of the orbit they once shared. The Helmi Streams are among the first known debris from a recognized ancient merger, identified not from any visible stream in the sky, but from the shared motion of scattered stars. From the pattern in velocity space that, once you know how to look, says this came from somewhere else. Then there is the Orphan stream. The name says almost everything. When it was identified, it was a trail of stars stretching across a broad arc of sky, clearly coherent, clearly a disrupted structure of some kind, and yet its parent was unknown. There was no obvious progenitor, no dwarf galaxy sitting nearby at the right position, no cluster whose destruction could account for it. The stream was there, identifiable, real, and the galaxy or cluster it had come from was simply missing. Not yet destroyed to the point of undetectability, simply not found yet, or perhaps already so thoroughly consumed that no coherent remnant remained. An orphaned trail, a scar with no wound visible. Later work has connected the Orphan stream to other structures and proposed candidate progenitors, but the name persists, and it is a good name because it captures something true about the enterprise. You find the stream first, the parent comes after, if it comes at all. Sometimes the trail is all that's left, And Palomar 5, if the Orphan stream is the ghost, Palomar 5 is the body in the process of becoming one. It is a globular cluster, a bound ball of roughly 10,000 stars orbiting the Milky Way at a distance of about 75,000 light-years, and it has tails, long, dramatic, tidal tails, stretching ahead of it and behind it along its orbit, visible in survey data as two great arms of escaping stars. The tails of Palomar 5 are actually longer than any reasonable estimate of the cluster itself. More of its stars are in the tails than in the core. You are watching a cluster disintegrate. You are watching in a single image the process that produced GD1, that produced the Helmi Streams, that produced every cold stream threading the halo. The same process, caught at an earlier stage, the body still present, but already hemorrhaging, already halfway to becoming a ghost. It will continue. Palomar 5 will, over the coming billions of years, lose the rest of its stars into those trails. The core will thin, the cluster will cease to be a coherent object, and what will remain is a long, cold stream curved along an ancient orbital path, carrying the chemical fingerprints of the environment where Palomar 5 stars formed, waiting for some future astronomer with an instrument more precise than anything we have now to read them and say, "This came from somewhere else." The star streams are patient, they wait. But now let us go further back. Let us go to the merger that, more than any other, shaped what the Milky Way is today. Because not all of the Milky Way's eating has been gentle nibbling at the edges. There was once a much larger meal. Gaia-Enceladus is the name given to it. It is also called the Gaia sausage, the second name arising from the characteristic shape its stars make in velocity space, a kind of elongated sausage-like distribution when you plot their radial velocities against their positions, very different from the more rounded isotropic distribution you would expect from stars born in place in the Milky Way's halo. The sausage shape is a signature. It tells you that these stars are mostly on radial orbits that plunge inward toward the galactic center and then swing back out rather than looping around more gently. And radial orbits, highly elongated orbits, are what you get when an object falls in more or less head-on or on a very eccentric path, rather than arriving on a graceful, circular approach. The merger happened roughly 8 to 10 billion years ago. At that time, the Milky Way was younger, smaller, still assembling itself. And it encountered a dwarf galaxy, not a tiny, ultra-faint one with 1,000 stars, but a substantial object, massive enough to be itself a significant piece of what was then the universe's galaxy population. That dwarf fell in, it was disrupted, its stars were scattered, and the evidence of it is still present today in the inner halo of the Milky Way, in the particular stars that move on those radial plunging orbits, diving toward the galactic center and then swinging back out over and over, frozen in that ancient trajectory, as if still feeling the original infall. The Gaia-Enceladus merger was not just large, it was transformative. The models suggest that this single event, this one ancient meal, was largely responsible for heating and thickening the Milky Way's disk. What we call the thick disk, the broader, more diffuse, older stellar population that extends above and below the thin disk where the Sun sits, may owe much of its structure to the energy deposited when Gaia-Enceladus fell in. The impact stirred things. It puffed the disk up. It contributed an enormous fraction of the stars we now call the inner halo. This one dwarf galaxy, consumed 8 to 10 billion years ago, reshaped the body our galaxy wears today. And a remarkable fraction of the globular clusters now orbiting the Milky Way were likely brought in by Gaia-Enceladus. Clusters that formed in that dwarf galaxy, traveled with it, survived the disruption of their host, and have been orbiting the Milky Way ever since. Not natives, immigrants, donations from a galaxy that no longer exists in any coherent form. There is something in this worth sitting with quietly. The idea that the Milky Way we live in, the disk we move through, the halo around us, the cluster system orbiting above and below the plane, is substantially the product of a meal that concluded billions of years before the Earth existed. We are not just living in the aftermath of ancient cannibalism, we are, in a very literal sense, made of it. The thick disk whose stars occasionally stir the dynamics of the region we live in, the inner halo stars that archaeologists study to reconstruct the Milky Way's past, the globular clusters that astronomers use to probe the structure of the dark matter distribution. Much of this is Gaia-Enceladus, dispersed, absorbed, transformed, become us. Some of the halo stars that carry the Gaia-Enceladus signature move in ways that are immediately recognizable once you know what to look for. The retrograde ones are particularly striking. Retrograde means they orbit backward, in the opposite direction from the Milky Way's general rotation, the great sweeping spin of the disk and most of its stars. The disk rotates in one direction. Most things in the disk go with it. But some halo stars go against the flow, arcing around the galactic center in the reverse direction. And for a long time, this was simply noted as a curiosity. A few odd stars with backward orbits. But the reason those orbits are backward is now understood, at least in broad terms. When a galaxy falls in from outside, it brings its own internal dynamics, its own orbital memories. If it falls in from a particular direction, its stars may end up on retrograde orbits once the dwarf is disrupted and its stars scattered. The retrograde orbit is the fingerprint of capture, a brand left on the star at the moment its home galaxy was consumed. It has been moving backward through the Milky Way for billions of years, all that time carrying the mark of where it came from. So you can go out tonight if the sky is clear, and if you have access to the data, and you can identify a halo star moving against the flow, and you can say, this one is not from here. This one arrived from somewhere else a very long time ago in a galaxy that no longer exists and has been circling our galaxy ever since, an immigrant still moving by the rhythms of its lost home. It is a quiet kind of archaeology, a quiet kind of strangeness, and Gaia-Enceladus is considered the Milky Way's last major merger. After that ancient event, the Milky Way settled into a calmer mode, still eating, still accreting, but in smaller bites, smaller dwarfs, more manageable pieces. The Sagittarius Dwarf is the most dramatic current example, and it is, compared to Gaia-Enceladus, a much smaller galaxy. We live in what is, by the standards of the Milky Way's history, a relatively quiet era. The great disruptive meals are in the past. What is happening now is smaller, slower, more patient. The fine work of consumption, still ongoing but gentler. Now let us talk about how all of this actually works, the mechanism. Because it is worth understanding, at least in broad terms, how a galaxy eats another galaxy, if only because the answer is so much stranger and quieter than the word cannibalism would suggest. The primary force is tidal force. You already know tidal forces in a different context. The Moon's gravity pulls on the Earth, and because the near side of the Earth is closer to the Moon than the far side, it pulls a little harder on the near side. That slight difference in pull across the extent of the Earth is what drives the ocean tides. Now apply the same logic to a dwarf galaxy falling through the gravitational field of the Milky Way. The Milky Way pulls on all the stars in the dwarf, but it pulls harder on the ones that are closer to the Milky Way's center and less hard on the ones that are farther away. The dwarf galaxy is not a rigid body. It cannot simply accelerate as a whole. The stars on the near side are pulled faster than the stars on the far side, and so the dwarf stretches. It elongates along the direction toward the Milky Way's center. Stars on the leading edge begin to drift ahead of the dwarf's own center of mass. Stars on the trailing edge fall behind. Over millions and billions of years, these drifting stars become the stream, the long, comet-like trail of debris following the orbit. There is no collision in the everyday sense. This is perhaps the most important thing to understand about the process, and it is also the strangest. When we say the Milky Way is eating a dwarf galaxy, we do not mean that two vast swarms of stars are crashing into each other, that there are flashes and explosions and destructions happening at every scale. We mean something far more subtle. The stars in the Milky Way and the stars in the dwarf are so far apart, light years between most of them, that two galaxies can pass through each other, and the probability that any individual star from one will actually collide with any individual star from the other is extremely low, almost zero. The Devouring is gravitational. It is the overall shape of the gravitational field that pulls the dwarf apart. No individual star in the Milky Way needs to touch any individual star in the dwarf for the dwarf to be destroyed. Gravity reaches across empty space and does the work at a distance. It is a silent process, almost entirely without violence in any physical sense. Billions of stars slowly rearranged, slowly unraveled, slowly absorbed, and nothing ever touching anything else. The largest structures in the local universe are being consumed by the architecture of curved space-time, and it is happening in near-perfect silence. There is another mechanism at work alongside the tidal stretching, and it has a wonderful name: dynamical friction. Imagine the dwarf galaxy moving through the halo of the Milky Way, which is not empty but is filled with dark matter and stars, thinly spread but present. As the dwarf moves, its own gravity reaches out behind it. It pulls slightly on the material it has passed through, creating a trailing overdensity, a subtle wake. Stars and dark matter that the dwarf has passed by are drawn ever so slightly toward the point where the dwarf just was. This means there is always behind the dwarf a slight excess of mass, and that excess pulls back on the dwarf. It is a drag force. It saps the dwarf's orbital energy. Very slowly, over countless orbits, this drag causes the dwarf's orbit to decay. It spirals incrementally inward. It falls gradually closer to the Milky Way's center. And as it spirals inward, it encounters stronger tidal forces which strip it more aggressively. Dynamical friction and tidal stripping work together, the friction drawing the prey inward, the tidal forces doing the unraveling once it arrives. And then there is the gas. For galaxies that arrive carrying a significant supply of gas, not just stars but the diffuse interstellar medium, the raw material for future star formation, there is an additional stripping mechanism. The Milky Way is not surrounded by perfect vacuum. Its halo contains a diffuse, hot plasma, gas that is much less dense than the gas inside galaxies, but spread over an enormous volume. As a gas-rich dwarf plunges through this halo plasma, the ram pressure of the collision, the pressure of moving through a medium like wind resistance, strips the dwarf's own gas away, not the stars. The stars are too massive, too individually bound, for ram pressure to affect them directly. But the diffuse gas is pushed off. The dwarf is swept clean of its star-forming material. It arrives carrying fuel. The Milky Way takes the fuel first. This is why the dwarf spheroidals, the Sagittarius dwarf, the Fornax dwarf, the Sculptor, and Carina and Draco and Ursa Minor dwarfs contain almost no gas. They are old, red, starless in the sense of making no new stars. Their gas was stripped long ago by ram pressure, by tidal forces, by the simple proximity to a larger galaxy. Without gas, they cannot form new stars. The stellar populations they carry are ancient. The stars born before the stripping, still orbiting, slowly aging, but no new ones being added. The dwarves are frozen. They are running on the stars they made before the Milky Way's influence reached them, and a dwarf that loses its gas loses its future. It becomes a purely stellar object containing only the stars already made, slowly losing even those to tidal stripping over time, until what is left is thinner and thinner, the stream longer and longer, and the remnant core smaller and smaller. The endpoint eventually is no remnant at all, only the stream. And the stream, over enough time and enough orbits, disperses and blends into the general halo, the individual stars losing their coherent motion, mixing with all the other halo stars, becoming indistinguishable from the ones that were always there. This is hierarchical galaxy formation. The idea that large galaxies like the Milky Way are not primordial objects. They did not arrive fully formed at the beginning of the universe. They assembled. They grew by accreting smaller objects, dwarfs, clusters, streams of gas, piece by piece over billions of years. The Milky Way is not a thing that has existed as it is now since the start. It is a thing that has been continuously built, continuously eating and incorporating and transforming, and is still doing all of that today. We are living inside the ongoing construction of our galaxy, and the construction material is other galaxies. The stellar halo itself, that diffuse cloud of old stars surrounding the Milky Way's disk, is thought to be largely the product of this accretion. The stars in the halo are old. They formed early in small dwarf galaxies that were then accreted and disrupted, their stars scattered into the surrounding space. Native halo stars, born in place in the Milky Way's own halo, certainly exist, but a large fraction, probably the majority, are accreted. They are immigrants. They arrived from outside, from objects that no longer exist, and they are now so thoroughly mixed into the halo that most of them are unidentifiable without the precise astrometry and spectroscopy that Gaia and its companion surveys provide. The stellar halo is the archive. It is the Milky Way's memory of every galaxy it has ever consumed, not a perfect memory. The older the merger, the more mixed the debris, the harder to read. But a memory nonetheless. Patient. Written in the positions and velocities and chemical abundances of billions of individual stars, waiting for us to become skilled enough to decipher it. And we are getting there. Slowly, fact by fact. There is something comforting in this if you let yourself settle into it. The idea that the history of our galaxy is not lost, that even the meals of 8 billion years ago leave traces, leave signatures, leave the faint chemical whisper of where they came from, preserved in stars still orbiting today. That the universe is, in a sense, more legible than it might appear, more careful with its records. The Milky Way ate galaxies before there were planets around any of its stars. It ate galaxies before the Earth existed. It ate the ancestors of the halo stars you see on a clear, dark night, pulled them in, unraveled them, scattered their constituent parts through the space we now inhabit. And it is eating still, Right now, this moment, the Sagittarius Dwarf's stars threading through the halo in their 360-degree stream, the Magellanic Clouds trailing their billion solar mass tail of hydrogen across more than 100 degrees of southern sky, the ghost streams threading the halo in their cold, patient ribbons, Palomar 5 hemorrhaging stars into its tails with every orbit. The mechanism is tidal force, the mechanism is dynamical friction, the mechanism is ram pressure, stripping away the gas before the stars. The mechanism is the simple, patient arithmetic of gravity applied across billions of years. And the result, the product, the thing being built is the galaxy we live in. Whatever you can see from where you are tonight, whatever portion of the sky is available above you, the halo around our galaxy contains, right now, the scattered stars of dozens of ancient meals, some of them identifiable, some of them blended beyond identification. All of them real. All of them here, orbiting, carrying their chemical tags and their orbital memories through the vast, silent space around our disk. The eating continues, the archive fills, and the Milky Way, as it has for 10 billion years, grows slowly larger in the dark. And now, the faint ones. Because what we have covered so far, the Sagittarius Dwarf mid-dissolution, the Magellanic Clouds trailing their river of stolen hydrogen, the cold streams threading the halo like threads pulled from a sweater. All of that is the visible part, the detectable part, the part where the prey is large enough or close enough or recently consumed enough that we can still make out its shape. But surrounding our galaxy in every direction, there are other companions. Quieter ones, smaller ones, some so faint that they have fewer stars than a medium-sized city has people. Some so dark that they are almost entirely made of something we cannot see at all. These are the ultra-faint dwarfs, and they are, in a way, the strangest objects in our sky. Galaxies so small and so ancient that they have barely changed since the first billion years after the universe began. The Milky Way is surrounded by dozens of known satellite dwarf galaxies, dozens, and the count keeps rising year after year as our instruments grow more sensitive and our surveys push deeper into the darkness at the edges of our gravitational reach. Think about what that means. Dozens of galaxies, each a separate gravitational entity, each containing its own population of ancient stars, each held together by its own halo of dark matter, each orbiting our galaxy the way a moth orbits a lamp. Most of them invisible to the naked eye, most of them requiring large telescopes and careful data processing to see it all. But there, when you look, real, present, some of them falling inward even now, beginning the slow journey that the Sagittarius Dwarf has already traveled so far along. And the smallest of them, the ultra-faint dwarfs, carry something remarkable. They contain as few as 1,000 stars. 1,000, that sounds like a lot of stars, until you consider that the Milky Way contains something in the range of 200 billion. So we are talking about a galaxy, something that has its own dark matter halo, its own gravitational identity, its own coherent structure in space, that holds roughly the same number of stars as you might count on a clear, dark night from a good mountain top if you had enough patience and a notebook. And yet these tiny, whisper-thin collections of ancient light are among the most dark matter-dominated objects we have ever found. That is the astonishing thing. They are not mostly stars, they are mostly invisible. The visible material, the actual stars you could photograph, might account for only a tiny fraction of the total mass. The rest is dark matter. Vast, cold, invisible halos of something we cannot directly detect, something we know is there only because the stars move faster than they should if the stars were all there was. Some of these ultra-faint dwarfs have hundreds of times more dark mass than visible star mass, hundreds of times. You are looking at an object that is, in terms of what you can actually see, nearly nothing. a faint scatter of old stars, most of them yellow-orange, cool, ancient, the kind of stars that have been burning steadily since before the Earth existed. And surrounding those few thousand stars, pulling on them, holding them in place against the tidal forces of the Milky Way, is a halo of dark matter that dwarfs, forgive the word, the visible content of the object it wraps. They are, as astronomers have called them, the most dark matter-dominated objects known, laboratories for the invisible majority of the universe, hanging at the edges of our galaxy's gravity like tiny, dark lanterns. Take Segway 1, it is one of the faintest galaxies ever confirmed. A small scatter of old stars, nothing that would catch your eye, even through a modest telescope if you didn't know exactly where to look. But it is held together. Its stars are moving in ways that betray a deep gravitational well far larger than the stars themselves could create. Segway 1 is almost entirely dark matter, with just enough stars to tell us that the dark matter is there. It is the dark matter that is the galaxy, really. The stars are just the part we can see, a small illuminated surface on something vast and invisible, and these stars are the stars in Segway 1. The stars in the other ultra-faint dwarfs are not random stars. They are chemically primitive. They formed early, in the first 1 or 2 billion years of the universe's life, from gas that had not yet been significantly enriched by many cycles of stellar death and rebirth. They carry the chemical signature of a very early cosmos. In the Milky Way's disk, where the Sun lives, stars have been processed and reprocessed for 10 billion years. The atoms in your body went through multiple generations of stellar furnaces before they ended up here. The heavy elements around you, the iron in your blood, the calcium in your bones, those were made in stars that lived and died before the Sun was born. The Milky Way's disk is chemically mature, enriched by billions of years of stellar generations. But in an ultra-faint dwarf, that enrichment barely happened. Star formation started, briefly flared, and then stopped. Quenched, starved, frozen. The stars that formed are the stars that remain. Old, metal-poor, pristine in a cosmic sense. When astronomers study their light and pass out the elemental ratios, they are reading the universe's early chapters, preserved in amber, barely touched by the subsequent 10 billion years. This is why the ultra-faint dwarfs are sometimes called fossils of the cosmic dawn, not metaphorically. Literally, they appear to have stopped evolving early and stayed that way, making them among the oldest surviving structures in the universe. The Milky Way has been eating galaxies for most of its life, and some of what it eats is older than almost anything in it. Eating these dwarfs, then, sprinkles the pristine material of the early universe into our halo. Every time an ultra-faint dwarf dissolves into the Milky Way's outer reaches, it adds a scattering of ancient, metal-poor stars to the halo, making the halo itself a kind of record of the early cosmos written in old light. Now, let me tell you about a few of them specifically, because they deserve to be named. Reticulum 2. Found in 2015 by the Dark Energy Survey, we'll come back to that instrument in a moment. Reticulum 2 is a small, faint dwarf sitting in the southern sky in the direction of the constellation Reticulum. It is remarkable for what its stars contain: enrichment in heavy elements, the kind of elements built in the most extreme environments in the universe. Neutron-star mergers, collisions between the densest possible stellar remnants, events of unimaginable violence lasting fractions of a second, but producing quantities of gold, platinum, and other heavy metals. The stars of Reticulum 2 carry the chemical fingerprint of one of those ancient explosions. Preserved in these old, quiet stars, locked into their spectra, is the record of a cataclysm that happened before the dwarf's own star formation fully took hold. Reading the stars of Reticulum 2 is like finding a document from before recorded history, still legible, still chemically specific, still telling you what happened. Antlia 2 discovered in 2018 in Gaia data. And what is remarkable about Antlia 2 is not its richness, but its absence. It is enormous in extent and far larger across the sky than you might expect for such a faint thing, and yet incredibly sparse. A ghost galaxy, truly, so diffuse that it had been hiding in plain sight, its stars spread so thinly against the background that the catalogue of stars was right there, in the sky, available to anyone with the data, and yet nobody had assembled those stars into a coherent picture of a galaxy until Gaia's precise measurements made the pattern visible. Antlia 2 hides behind the plane of our own galaxy, in the confused region where our own disk's stars crowd the view, and it is so spread out and faint that it simply did not register as a separate object until the data was good enough to find it. A galaxy hiding behind a galaxy. There when you know how to look, and not there at all when you don't. Crater 2, found in 2016, another enormous faint, low-density dwarf. They're one of the lowest surface brightness galaxies ever measured, so transparent, so sparse, that it has been described as a galaxy you can almost see through. Its stars are spread across a region of sky large enough that, if you could somehow illuminate it to naked eye visibility, it would cover an area far larger than the full moon. But its actual brightness is so low that it was invisible until modern wide-field surveys made it findable. A galaxy you can see through, made of stars and dark matter and ancient light, real and present, and nearly transparent. And then there are the ones named for the constellations they appear to inhabit, which is simply a naming convention. The constellation is just a locator on the sky, a human pattern we've laid over the celestial sphere to organize our view. The Bootes dwarf, Hercules, Leo Thulta, Leo Fifth, Coma Berenices. Each of these is a separate ancient object, a separate small collection of old stars held in a dark matter halo, each orbiting our galaxy, each faint enough to have required the modern era of wide-field digital sky surveys to find. Imagine, you are standing in a field at night and you know because the data tells you that in the direction of a certain patch of sky, let's say toward Bootes, the herdsman, there is a galaxy. Not a smudge visible to your eye, not something a small amateur telescope would show you, but a galaxy. Thousands of old stars and an enormous dark matter halo right there in that direction, present, real, moving in concert with the Milky Way's gravity, slowly orbiting, ancient. That is what these objects are, and they have been there the whole time. Then the classical ones, the ones that were found first, when surveys were less sensitive and so only the brighter satellites were visible: Fornax, Sculptor, Carina, Draco, Ursa Minor. These are the dwarf spheroidals that defined the category, the ones astronomers came to understand first, as a distinct class of object. The Fornax dwarf spheroidal is one of the larger and brighter of these, bright enough that it was recognized decades ago as a separate galaxy. It is unusual among its peers because it hosts several globular clusters of its own, a small galaxy with its own smaller gravitational children. Most dwarf spheroidals have no globular clusters at all. Fornax has several. This makes it something of an outlier, a dwarf wealthy enough in its own small way to have kept its own satellites: the Sculptor dwarf, Carina, Draco, Ursa Minor. These are quiet objects, gas-poor, dominated entirely by old stars, no ongoing star formation, no bright nebulae, no active stellar nurseries. Just the steady, cool light of stars that formed billions of years ago and have been burning steadily since, too far from the Milky Way's center to have been fully disrupted, but close enough that they gave up their gas long ago, the stripped, quiet survivors. Draco holds a particular place in the history of this field, because it was one of the first dwarf spheroidals recognized as dark matter-dominated. The stars of Draco move faster than the visible mass can explain. The stellar mass is there, you can count the stars, estimate their masses, calculate how fast something should be orbiting in that gravitational well, and the stars are moving too fast. There is more gravity than there are stars. There is something else there, invisible, holding the whole thing together, pulling on those ancient stars. Dark matter. Confirmed in this quiet little object by the simple arithmetic of velocity and gravity. Draco helped establish that ultra-faint and dwarf galaxies are not merely small. They are dark matter-dominated in a way that makes them unique windows into the universe's invisible majority. Leo Tophi and Leo that can orbit at the edges of the Milky Way's gravitational reach, among the most distant of the classical satellites, pushing toward the boundary between bound satellite and escaping object. Leo Y in particular moves fast enough that its status as a permanently bound satellite has been questioned. It may be drifting slowly outward, barely held, or it may be bound, for now. The margins here are real, and astronomers continue to refine the measurements that would tell us for certain. These classical dwarfs, Sculptor, Carina, Draco, Ursa Minor, Fornax, Leo I, Leo II, were recognized as a family long before the ultra-faint discoveries of the 2000s and beyond. They defined what a satellite dwarf galaxy looked like before the surveys got deep enough to reveal just how many more there were waiting at the lower end of the brightness scale. And those surveys. Let me tell you about the instruments that changed everything. The Sloan Digital Sky Survey, SDSS as astronomers call it. Beginning systematic observations in 2000 and running through subsequent years and phases, it imaged roughly a third of the sky in multiple colors, cataloging hundreds of millions of objects. It was not built specifically to find dwarf galaxies, but it was sensitive enough and it covered enough sky that it began turning up satellites that previous surveys had missed entirely. In the 2000s, a wave of new faint dwarfs was discovered in SDSS data. Dwarfs in Canes Venatici, in Coma Berenices, in Leo, in Ursa Major. Each one found by looking for a subtle statistical overdensity of faint old stars at a common distance, a pattern too faint for older surveys but just visible in SDSS's deep images. The Dark Energy Survey, DES, pushed further, particularly into the southern sky, including the region around the Magellanic Clouds. When DES began releasing its early data in the mid-2010s, more satellites appeared. Reticulum too, as I mentioned, others, and a cluster of them appeared suspiciously close to the Magellanic Clouds themselves. Small dwarfs that might be satellites of the clouds rather than independent satellites of the Milky Way, galaxies that the Magellanic Clouds brought with them when they began their own approach to our galaxy. A small galaxy with smaller galaxies of its own, all of them now falling together into the Milky Way's gravitational embrace. If that is what those objects are, and the evidence is suggestive, then the Magellanic Cloud system is not just two galaxies, but a small group, a mini cluster of its own, now being absorbed by a larger structure. The clouds didn't just bring their gas when they came, they may have brought their families, and the next instrument. The Vera C. Rubin Observatory, named for Vera Rubin, whose work on galactic rotation curves in the 1970s helped establish that dark matter must be present in galaxies. The Rubin Observatory, beginning its systematic legacy survey of space and time in the 2020s, will image the southern sky repeatedly to extraordinary depth. It will be sensitive to objects far fainter than anything current surveys can reach. Astronomers expect it to find many more satellite dwarfs, tens perhaps, or even more, lurking at the faint edge of detectability, invisible to current instruments but present in the Milky Way's gravitational reach. the map of our galaxy's satellite family is going to get considerably more crowded. The count of known satellites went from roughly a dozen in the 1990s to roughly 50 or more today. With Rubin, that count may expand dramatically. Most of the family, quite possibly, is still unseen. This brings us to something called the missing satellites problem. Simulations of how galaxies form in a universe dominated by cold, dark matter, the leading model, built up over decades of cosmological work, predict that a galaxy like the Milky Way should be surrounded by many hundreds or even thousands of small dark matter subhalos, each potentially containing a small galaxy. But we only see dozens. The prediction outruns the observation by a large factor. Where are the missing satellites? There are several possible answers. Some may be entirely dark, halos of dark matter that never managed to gather enough gas to form stars at all, completely invisible because they have no stars. Some may exist, but be too faint to have found yet, waiting for Rubin's survey to reveal them. And some may have been there once, tiny and fragile, but destroyed in the early universe when something very energetic swept through. That something is reionization. In the first billion years or so after the Big Bang, the universe's first stars and quasars flooded space with intense ultraviolet radiation, stripping electrons from hydrogen atoms across the cosmos. A phase called reionization. For very small dark matter halos trying to accumulate gas and form stars, this was catastrophic. The radiation heated the gas, preventing it from cooling and condensing. Many small halos may have been starved before they could form significant stellar populations, leaving them either completely dark or containing only the few stars that managed to form before the radiation arrived. This is the hypothesis for reionization quenching, that the faintest, smallest dwarfs may be ancient, arrested objects, frozen in the act of becoming galaxies, their star formation shut off by the universe's own early light before they could grow into anything larger. Which means that studying them is not just interesting astronomy, it is a way of reading the conditions of the universe's first billion years, preserved in these tiny, quiet, ancient objects. They froze early, and in freezing they preserved something. The ultra-faint dwarfs then sit at this peculiar intersection. They are the smallest, faintest things we call galaxies. They are among the oldest, most primitive objects in the universe. They are overwhelmingly made of something invisible, and they may be the remnants of a much larger population that was starved into darkness by the universe's own first light. Finding them, counting them, measuring their stars and their dark matter halos is one of the primary ways we have of testing our theory of how the universe assembled itself. And the Milky Way is slowly eating them. One by one, those that orbit close enough and long enough, tidal forces stretching them, dynamical friction dragging them inward, ram pressure stripping their gas, if they still have any, and eventually, over billions of years, dissolving them into the halo. Now, before the zoom out, before the quiet that is coming, there are two more things I want to tell you about. The first is Omega Centauri. You may have heard of it. It is the largest globular cluster orbiting the Milky Way, a dense, spherical ball of roughly 10 million stars, sitting about 17,000 light-years away, bright enough to be visible to the naked eye from the southern hemisphere. It is an extraordinary object in its own right, a glittering swarm of ancient stars that has been known and studied for centuries. And for most of that history, it was classified simply as a globular cluster, the largest and most impressive of the Milky Way's collection of such objects, but a cluster nonetheless. But Omega Centauri is strange. Normal globular clusters contain stars of essentially one age and one chemical composition. They form from a single cloud of gas at one time, and all the stars reflect that single origin. Omega Centauri contains stars of multiple ages and multiple chemical compositions. It has a spread of stellar populations, a variety that shouldn't be there in a simple cluster. The stars of Omega Centauri tell different stories, as if they formed at different times from different material, as if they represent multiple episodes of star formation rather than one. The leading explanation is that Omega Centauri is not a globular cluster at all. It is the stripped core of a dwarf galaxy, a galaxy the Milky Way consumed long ago, whose outer stars were peeled away into the halo by tidal forces, leaving only the dense nuclear heart. What we see when we look at Omega Centauri may be the compressed remnant of a once larger galaxy, everything external already absorbed, only the nucleus surviving, a tombstone in a way, or perhaps better, a gravestone that is still standing while everything around it has dissolved. The Milky Way's cluster collection is, in this reading, partly second-hand. Some of the globular clusters orbiting our galaxy were donated by the galaxies we ate, transferred to us in the consumption, continuing to orbit in the new environment of a larger host. The Sagittarius Dwarf donated M54, the cluster that Messier catalogued in 1778, without knowing its origin. Omega Centauri may be the donated core of an even earlier meal. The Milky Way collects these objects and keeps them orbiting, ancient, carrying the evidence of where they came from. And the second thing, the Sagittarius Dwarf, in its repeated orbital passages through our galaxy, does something else. As it swings through the Milky Way's disk on each orbit, it disturbs it. The passage of a massive object through a rotating disk of stars and gas creates ripples, gravitational waves spreading through the disk. Waves not in the sense of the space-time waves from merging black holes, but physical oscillations of the disk's structure. Waves in the heights of stars above and below the disk's midplane, traveling outward. The Milky Way's disk shows a warp. The disk is not perfectly flat but bent, curving above and below its average plane in different directions. And it shows vertical waves, a ripple-like structure of stars oscillating up and down as if something struck the disk and set it ringing. Some astronomers link these features to the passages of Sagittarius and to the gravitational influence of the Magellanic Clouds. The galaxies being eaten leave the eater trembling, very slightly, long after each passage. Think of a quiet pond and someone dropping stones into it from two directions at once. The waves spread and interfere, and the surface that was still is now subtly moving, the motion propagating outward, carrying the memory of where the disturbance came from. The Milky Way's disk is something like that pond. The ripples are there, in the data, measurable by Gaia and by other surveys. And they may be the record, encoded in the vertical positions and motions of billions of stars, of every time the Sagittarius Dwarf came through. The eaten galaxy leaving its mark on the eater's body. A reciprocal disturbance written in the structure of the disk, perhaps billions of years after it was made. Close the books on the catalogue for now. The objects have all been named. The mechanisms are all in place. Let the facts rest, because what remains is the thing underneath all of them.
You have been lying here, or wherever you are, in whatever room or corner of the world, Edik, while the stars have been going on outside without waiting. And what I want to tell you now is what it all adds up to.
A fully digested dwarf galaxy does not disappear. Not quite. It becomes instead something more distributed. The stars that were once held together as a coherent object, orbiting a common center, identifiable as a single thing, are stretched by tidal forces over hundreds of millions of years into a stream. Then as the stream orbits and the Milky Way's own gravitational irregularities perturb it over billions of years, the stream broadens, and the individual stars diffuse outward, and the orderly pattern becomes a subtle, statistical excess, and eventually even that becomes indistinguishable from the general halo. The galaxy's identity dissolves. The stars are still there, but they are everywhere at once. A single eaten dwarf, after enough orbits, can have its stars spread across the entire sky. Not metaphorically, literally. Stars that were once part of the same small galaxy, orbiting the same center, now scattered across different quadrants of the night, separated by tens of thousands of light years, no longer adjacent, no longer connected by anything visible, but still sharing their chemical fingerprint, still carrying the same elemental ratios set when they formed, in the same cloud of gas, in the same now dissolved galaxy. Chemical tags that identify them even across the sky as siblings. Some of the halo stars around us may be Sagittarius's children. Some may be from the Gaia-Enceladus merger, 10 billion years old, orbiting on their long radial plunges in the inner halo. Some may be from mergers we haven't yet identified, from galaxies so thoroughly digested that we haven't found enough of their stars together to recognize the pattern. The halo in every direction is full of these immigrants, these guests that arrived billions of years ago and never left. And the faint glow of the stellar halo itself, too dim for the naked eye, a ghost of light surrounding the disk, is the accumulated, blended light of every galaxy the Milky Way has ever consumed. Every merger, every tidal disruption, every ancient passage of some smaller system through our galaxy's gravitational field left stars behind, and those stars are still out there, still glowing, still orbiting. The halo is not merely a region of space, it is a memorial, a slow accumulation of everything our galaxy has eaten, still softly luminous in the dark. You cannot see it tonight with your eyes wherever you are. But it is there, surrounding the disk that contains our sun, in every direction, in every part of the sky you might look toward, the ghosts of galaxies orbiting.
And some of those stars up there, the ones visible tonight, in the portion of sky available to you, some fraction of them are not originally from our galaxy at all. They arrived here as part of an infalling dwarf, were stripped away by tidal forces, were scattered across the halo, and have been orbiting with the rest of the Milky Way ever since. Immigrants, indistinguishable from natives.
You would need their chemical tags, their stellar spectra, their orbital parameters to tell them apart from stars that formed in our own disk. The night sky is more mixed than it looks. And then there is the matter of what you are made of. The gas that the Magellanic Stream carries, roughly 1 billion solar masses of hydrogen trailing across more than 100 degrees of sky, will eventually fall inward. Not soon, not in any human-relevant time frame, but cosmically that gas is moving, pulled by the Milky Way's gravity, and at some point in the future it will rain down onto the disk and it will mix with the gas already there, and some of it will condense into molecular clouds, and some of those clouds will collapse under their own gravity, and stars will form. Stars that exist because a pair of companion galaxies trailed their gas across the southern sky for billions of years and eventually let the Milky Way take it. The eaten galaxy's gas becomes tomorrow's stars, and the atoms in those stars, after they live and die, become the material of future planets. And perhaps somewhere in that unimaginable future, the atoms that were once part of the small Magellanic Cloud, part of the bridge of gas between the clouds, part of the Magellanic Stream draped across the sky tonight. Perhaps some of those atoms become the building blocks of something that thinks and wonders. We are already, in a smaller way, made of this story. The Milky Way has been eating dwarfs for 10 billion years. The halo stars that were scattered from ancient mergers contributed to the chemical enrichment of the galaxy over time. The gas stripped from infalling galaxies contributed to star formation episodes. The stars that formed in those episodes contributed to the interstellar medium, and eventually to the disk, and eventually to the solar nebula, and eventually to the Sun and the Earth and everything on it. Some fraction of what you are arrived here, because the Milky Way is, and has long been, a galaxy that eats other galaxies. The cannibalism is in you quietly in whatever small atomic fraction is traceable back to an eaten dwarf. Not in any way you can measure or feel, but in the way that everything in the universe is connected to everything else through the long, patient chains of cause and effect that run back to the beginning of time. We are made of the slow meal. That is perhaps the most extraordinary thing about all of this, and it is also strangely the most calming. The violence implied by the word cannibalism is entirely misleading. There is no violence here. There is no crash, no catastrophe, no moment of impact. The dwarves fall inward over hundreds of millions of years. Their stars are pulled gently apart by tidal forces, spread across the sky in thin, cold streams, scattered gradually into the halo. Their gas is stripped slowly and trails behind them like the tail of an enormous comet. The whole process is conducted in near-perfect silence, in near-perfect emptiness, at speeds that dwarf anything human but are achingly slow by cosmic standards. It is the quietest thing imaginable, a galaxy a tenth of our size, falling slowly inward over billions of years, its stars pulled out one by one in the cosmic sense, not one by one in the human sense, not even in the astronomical observation sense, but gradually, statistically, orbit by orbit, each passage through the disk costing the dwarf a little more of itself, until eventually what was a galaxy is a stream, and what was a stream is a diffuse enrichment of the halo, and what was a separate thing is now part of something larger and cannot be distinguished from it. That dissolution is the end of the story for each dwarf. But it is not destruction. It is transformation. The stars are still there, the atoms are still there, the chemical tags are still there. The dark matter halo may continue orbiting long after the stars are scattered, an invisible ghost of the galaxy that used to be, still pulling very slightly on the space around it, still present in some sense even after every visible trace is gone. And the Milky Way, incorporating all of it, grows, not rapidly, not dramatically, slowly. Billions of years to become what it is, billions more to become what it will be, a galaxy built from galaxies, assembled over deep time by the patient arithmetic of gravity. The story has been going on for longer than the Earth has existed. It will continue for longer than the Earth will exist. We are here, briefly, in the middle of it. And tonight, wherever you are listening from, in whatever room, in whatever city, in whatever country, in whatever corner of the night, tonight, the Sagittarius stream is there above you, if you could see it. A ribbon of stars wrapping 360 degrees around the entire Milky Way, torn from a galaxy that is still, right now, losing itself into ours. The Magellanic Clouds are rising or setting somewhere over the southern horizon, trailing their river of hydrogen across more than 100 degrees of sky. The halo surrounds you in every direction, softly glowing with the light of every galaxy we have ever consumed, a memorial and a history in the same faint luminescence. You are inside the act of one such meal. Not metaphorically, literally. The stars of the Sagittarius Dwarf thread through the halo space around our galaxy right now. The gas of the Magellanic Stream falls slowly inward. The ultra-faint dwarfs orbit at the edges, ancient and dark and patient, waiting for the tidal forces to begin their slow work. And you are here, in the middle of it, lying in the dark, in a room that sits on a planet that orbits a star, in a galaxy that is, slowly and silently, consuming its neighbors. And that is, somehow, a good thing to carry into sleep. Not because it makes you small, though of course in scale it does, as it makes everything small except the scale itself, but because it means you are not separate from any of this. The same processes that built the Milky Way by eating dwarves, built the solar system, built the Earth, built the conditions in which anything like you could exist. The eating is not happening to you from outside. You are, in some small, atomic, and historical way, part of it, made of it, continuous with it. The universe is not doing something to you. You are something the universe is doing. Back at the beginning tonight, whenever you started listening, wherever you were when this began, I asked where you're listening from, what time it is in your corner of the world. And I wonder now, at the end of this long, slow drift through the eaten galaxies and the cold streams and the ghost dwarfs and the blended ancient light, I wonder if the sky outside looks any different to you than it did before. If you were to step outside right now, or simply to look toward the window, or simply to know, in the quiet of wherever you are, that the halo is out there, in every direction, full of the scattered stars of things that used to be galaxies and are now part of ours. It's all still there. It was always there. We just didn't have the words for it, most of us, until tonight. If this slow journey through the sky's quiet cannibalism has been good company tonight, a like and a subscribe would mean a great deal. Small creators like me genuinely rely on your support to keep making these, and it helps more than you might think. And if you'd like to leave something in the comments, tell me where you're listening from and what time it is in your corner of the world. I love knowing.
I love imagining the different darknesses you're all lying in, the different pieces of sky above different rooftops and windows and open fields, all of them part of the same halo, all of them carrying the same faint, ghostly light. Sleep well, wherever you are. Close the books, dim the lamp. Class is over, sleepy scholar.